So, good afternoon, or exactly noon, or something. I see some new faces, so can I ask you guys who is not part of CSAAW? Just to have some here that I see that are new, or so just for you guys to know, CSAAW is basically these meetings that we have every 2 weeks to discuss complexity, and there are people in different departments, a lot of computer scientists, a lot of physicists, mathematicians, and social scientists and everything, and we try to discuss things that are in common between the things we do, and we basically love complexity. And every 2 weeks we have these meetings, and you can be part of CSAAW, and if you are, you can order food. When we send the emails around, you can put your name, and you're going to have food waiting for you on the back. So today we have Abe, who is talking about predictability or unpredictability. And so the floor is yours.
Yeah. Just real quick, I saw some hands for people who aren't directly involved in CSAAW. What brings you here today?
We saw that the name of the talk seemed really interesting. So,
Where did you see it?
It told you, man.
I signed up for the group during basketball. But
Gotcha. Okay, cool. Glad to have you here today. I'm Abe Gong. I am in the Department of Political Science and Public Policy and Complex Systems, so I'm one of the interdisciplinary people who wouldn't have a home if it weren't for CSAAW and Complex Systems. Today I'm talking about something that is totally unrelated to my own research. So this is just a topic that's been on my mind for a while. These are things that we often talk about in complex systems, and I thought it'd be fun to bring them together. I'm filling in for another speaker today. So if there are gaps or holes in this, bear with me, raise your hand and correct me if I'm wrong. I'm going to try and approach these things at a pretty high level. I'm not going to show any equations. I'm not going to get into the guts of the math. I just want to indicate that these kinds of proofs are possible. So, yeah, we'll go with that. The topic for today is predictable unpredictability. And so my goal here is to talk about times when you would not expect to be able to predict the outcome of a system, usually a dynamic system. So let's ground this a little bit of philosophy of science. Almost all scientific disciplines start with prediction of one kind or another. This isn't the only philosophy that makes science work, but it is a very powerful one. So, will it rain tomorrow? Will this medicine help my patient get better? Will my bridge fall down if I build it to such and such specifications? These are scientific questions that we want to know answers to. And most scientific disciplines grow up around successful prediction of something or another. Now, I should point out, some of these things are things that we can predict pretty well, like who will win the election in November. Most elections, political scientists can predict that pretty well. This election turns out to be a hard one when you look at it as sort of a borderline case. Do we go Republican, do we go Democrat? It's almost 50-50. But we're actually pretty good at predicting these things. On the other hand, you can take other questions like, when will a revolution happen? Just pretty similar, right? One group moves out of power in government, another group moves into power. We have no success at predicting revolution. We're really bad at that. So, for some reason, we can predict some kinds of government transfers of power, and we can't predict others. Now, why is that? Philosophically, there are two positions you can take here. One is, well, if we just understood it a little bit better, if we could just do better public opinion polling in Libya, then we'd be able to predict where the government would be in a few months. The second option is a little bit bleaker. It's, no, there's no way we could predict that ever. Even if we had all the available information, we would never be able to predict when a revolution is going to happen in a given country. Now, I don't know in terms of revolution which of those is true, but it's interesting to contemplate the possibility of unpredictable problems. For a long time, people assumed that if you got enough information, or if you could understand the dynamics of the system well enough, then of course you'd be able to predict it. And what I want to show you today is 3 reasons for thinking that that might not be true. 3 totally different lines of proof that'll get you to the point of saying, oh, yeah, X, that thing that we want to predict, it's hopeless. We're never going to be able to predict it. So for each of these, I'm going to try and give you some basic intuition. I'll give you some examples. I have little demos that hopefully will make these things a little bit more easy to understand. And then I'll also talk about counterexamples. Let's see, anything else? Oh yeah, I also have resources and links for future use. So we'll upload the presentation, and then hopefully that can be a resource for people. Now let me make a quick note on this, going back a slide. No, we'll go back a slide. Throughout the presentation, I've got these little ... question mark things. The question mark disappeared here, I don't know why. Anywhere you see that, I have a list of examples, and I'm looking for other examples. So if you want to scribble down other examples of things that we try and predict with science, or later on, chaotic systems, or problems that are computationally complex, go ahead and do that, because we'll put them in the presentation. I'll gather notes and suggestions from you at the end. We'll put those in the presentation and go from there. Does that make sense? Anywhere we have ... question mark, I'm looking for suggestions, either in the Q&A or just in notes later on. Okay. So things that are fundamentally unpredictable. Let me start by shooting down a straw man, or burning a straw man, or whatever. This may not work. It looks like it's not showing up properly.
I think it's you've got an initial condition on one lot. It's an electric cable that
No, I tried this out just before I came here, and it didn't. This is what we get for switching computers. Okay, well, if this were working properly, what you would see is a logistic map that takes a point on this curve and then projects it across to the other side of the curve and then projects it up from there, which is a really lousy way of explaining this. You know what, I'm going to skip this because it's not going to help. How do we get back into the presentation on this wonderful Mac?
Click on the right. There's start presentation. Right.
I'm not in Keynote.
So there is a start presentation on the right. Maybe click on the start that current
Okay,
slide.
so it's going to kick us out every time we.
If I start that current slide.
Okay. I'm trying to think quickly if there's an easy demo we can do on the chalkboard. There's no chalkboard. Okay, that makes it easy. Chaotic systems. Small initial conditions lead to big mistakes in prediction later on. The graph down in the corner here is a very famous chaotic system. It's the Lorenz system, which it turns out is a pretty good description for weather. So weather systems tend to look like this.
Maybe you're probably going to talk about that, but when you say the unpredictability of chaotic system, if you are close enough to the initial conditions, you have some range of predictability, right?
Yes.
So if you think about coming with a model, it's kind of time dependent on how far you are from the initial conditions.
Yes, that's exactly right. So I'm not going to get into the details on this, but if you talk about Lyapunov exponents, this is what you're thinking of, right? You can predict basically for a given amount, this is a layman's definition, but for a given amount of initial error, how long will it be until your predictions are totally out of whack? And so, for example, let's do examples. You can talk about the weather. Turns out that our prediction horizon on the weather is really pretty short. It's on the order of a few days or weeks at most for the level of accuracy that we're able to get for how air and moisture and other things are swirling around in the atmosphere. For other things like predicting where planets are going to be, it turns out that that's also a chaotic system when you have multiple orbital bodies all tugging on each other. Outside of a certain, after a certain horizon, we just can't have accurate predictions on where the planets are going to be because we can't measure them precisely enough. But that event horizon, if you want to call it that, is several hundred years out. So something can be chaotic, and that doesn't mean that it is not predictable at all. In the short run, we can predict it pretty accurately. It's just over time, the errors balloon, And in the long run, there's no way of predicting.
So in your example for weather, like if you're doing some prediction using rainfall, so you said if you're looking 2 months before my case is in malaria, so I'm wasting my time because it's unpredictable, like it's not a good predictor.
Yeah, that's the gist of it. And not only is it not a good predictor, but because of the dynamics of the system, no good predictor is possible.
So because the weather is chaotic, it's not a good predictor.
Because the weather is chaotic, many aspects of the weather are just fundamentally unpredictable outside of a certain time horizon. Okay, so just real quick, does anybody have other examples of systems that have been proven to be chaotic? I was looking for a list of these, and I couldn't. These are the ones I knew off the top of my head, and I couldn't think of any others.
So this isn't so much a often modeled system that's proven to be chaotic, but I was thinking from your logistic map example, that and the tent map are pretty much, one way you can think about it is that like kneading bread, right? You stretch it out and you fold it over. So if you're trying to make something in that kind of particular process, the positions of your initial stuff will follow chaotic.
Okay, that is an awesome way of explaining that demo that didn't work. So if you were to take a lump of bread and draw a little mark on it, stretch it out and fold it over, stretch it out and fold it over time, if you have one mark and then another one next to it, those marks are going to spread out until they're nowhere near each other. So the initial conditions that were very close eventually end up spread out all over your loaf of bread. Great example.
Double pendulum is also really fun.
Yep.
And any fluid flow that's not in a laminar regime.
Yep. So double pendulums, non-laminar fluid flow. I have always been intrigued that there are no social science examples here. So social scientists sometimes talk about chaos, but they're not using it in the correct technical sense. And it strikes me that if you were careful, you could probably construct a game or a political system or something, or rather a model of that falls into the category of chaotic equations.
I think under some parameter regimes, the alpha roll will get you chaotic dynamics in the number of people going to the bar.
That's interesting. That's cool. Okay.
You could put 2 people inside a lot of bread. Keep them.
Right. Yeah, I don't know if that's chemistry or
Maybe both.
social science or what. Yeah. Interesting.
Grad school seems pretty chaotic.
It does. It does. Well, I mean, there are all these social systems that seem pretty crazy, seem pretty chaotic in a lot of ways. And as a social scientist, it would kind of be nice to say, you know what? Elections of such and such a type are fundamentally unpredictable. We'll be able to predict this one with this much accuracy, the next one with that much accuracy, and then after that we've crossed the event horizon and it's hopeless. But we don't have that. It strikes me that it's probably possible. So if anybody's looking for a dissertation topic, that's one of the ones that I kind of abandoned along the way. Cal?
So because looking at age especially twins in academy, it's almost like having the same person, just to step aside on the
Yeah, that's interesting. To the best of my knowledge, all of those studies, I've never seen one of those studies that's not a statistical study. So it's starting from the assumption of randomness. They're not trying to prove chaos. They're just saying these 2 people have a lot in common, and now we're going to run a statistical estimator. But yeah, maybe if you were clever, you could use a way, you could come up with some way of thinking of that as nearby initial conditions and turn that into a dynamic chaotic system. Okay, let's keep going because we've got 2 more of these. No, actually, let me step back and raise an intriguing counter-argument to this. So in the bottom, we have a 1950s picture of an imaginary weather satellite. And it turns out that chaotic systems in general, not all of them, but many of them have this interesting property that since the state space is small, so the number of different kinds of weather that you can get is pretty small, but you never reach exactly the same place twice, you have this strange attractor, this loop of how things are going to unfold over time. It turns out that has to be coiled in on itself very, very close, which means that a small change can nudge you back to a previous path, or back to a different path. So you can use the fact that small changes lead to very big outcomes in the end to make very small change, to nudge the system in very small ways that make it behave as if it weren't chaotic. So if you really understand the dynamic of the system, you can constantly be putting in these small nudges that keep the system stable, even though it ought to be chaotic. So it's chaotic plus epsilon equals stable. Intriguing possibility. And in that case, the whole argument about chaotic systems being unpredictable falls apart, because we've got a chaotic system and we're nudging it just a tiny little bit, and now all of a sudden it behaves in a predictable way. I should have ... question mark here. If anybody has ideas for other vocabulary or resources or things to look up for chaos theory, I'd love to see them. This is really, really sketchy, really brief. The first resource here, the Computational Beauty of Nature, has a great set of chapters in the middle that explain chaos theory more elegantly and more clearly than I've seen anywhere else. So if you're going to make one stop to read more on this, I'd suggest going there. Okay, next, complexity theory. So this complexity theory comes out of computer science, and the intuition is that some kinds of problems are extremely hard to solve. In principle, we know exactly how to solve them. You can go through a number of steps, and you'll always get to the right answer. You guys know the Rubik's Cube solution, where if you go through a certain series of motions over and over again, the Rubik's Cube always ends up solved. It might take you a long time, but if you just do A, B, C, D, E over and over again, eventually it ends up solved. Similar thing here. We know exactly how to get the answer to a problem, but actually carrying out that computation can take a very, very long time. So if predicting a system requires solving a computationally difficult problem, and a long time, whatever that is too long, then the system is, for all intents and purposes, unpredictable. So let's give a few examples of problems that fall into this class. Probably the most famous is the traveling salesman problem. So the intuition here is you have a bunch of cities, and they're all some distance from each other. You have a salesman who needs to go and drop off a washing machine in each one of those cities. And the question is, what is the quickest way to visit all the cities and drop off all the washing machines? It turns out that finding the answer to that question is really hard. It takes a long time to go through and look at all the possibilities and figure out what the right answer is. You can prove that there's no shortcut for the general problem there. And so because of that, if you assume that looking at any one solution and evaluating it takes some small increment of time, you can prove that it will take a long time to solve that problem perfectly. That's the traveling salesman problem. An even more difficult problem is the halting problem. This is from the very beginning of computational complexity theory. The question is, given an arbitrary set of computer code, if I run it with an arbitrary input, will it halt? Will it stop? Or will it get stuck in an infinite loop and run forever? And it turns out that you can prove that there is no algorithm for solving the halting problem in every case. Loosely speaking, the quickest way to know for any given case is just run the program and see. So you can prove that there is no clean solution to the halting problem. Lots and lots of algorithms or problems that you'd like to run on a network turn out to be very difficult, or NP complete, difficult to answer. And intriguingly, cellular automata also turn out to have this property. And there are a lot of other things that do too. Who's familiar with cellular automata? Just a quick show of hands. Who's seen this before? Okay. Let me show you a quick demo that involves CAs. So, who knows Conway's Game of Life? And anybody feel up to giving a quick explanation on how it works? You've already answered, Maria.
You have a grid, and on the grid you either have cells that are live or dead. If they're dead, they're empty. If they're live, they're occupied by a circle or a square. It's just a filled-in spot. And depending on how many of the surrounding cells are either living or dead, the cell will either live or die, or if it's a dead cell, then it might become alive.
Yep, that's exactly right. So what happens when you actually run the Game of Life? I mean, did they just all die? Did they all come to life? Does it sort of spread out from one point?
Sometimes it usually just like fans out, and it usually ends up with just like a couple spots still functioning, still just kind of alternating between some stable configurations and some non-stop. You can have other configurations where like it'll shoot off like a moving set of like
A glider.
kind of flyer will still go across the screen.
Yeah, that's exactly right. So Conway's game of life is a special case of cellular automata, and what I'm going to show you here is a computer built inside Conway's game of life. So this whole grid is set up. It is Conway's game of life, but they've gone through and they've programmed it so that you have streams of bits flowing through in the form of gliders and logical gates that are certain configurations that when they get hit by a glider, they either emit or do not emit other gliders. It's really pretty fascinating to watch. So this is zoomed way out on the whole system, and now we're zooming in to get a finer grained look at it. And there it is. This is Conway's game of life. So you have bits of information flowing back and forth. The timing is just right. Down here you have some logic gates that are receiving or not receiving gliders. And based on this, you can build a whole computer inside Conway's game of life. So if you wanted to, you could program a computer with a bunch of these bits that would actually be programming Conway's game of life inside Conway's game of life. It's a universal computer. And because of that, it turns out that this falls into one of those really difficult to solve classes of problems. And so provably, there is no clean way to predict how Conway's game of life is going to turn out. So game of life and many other cellular automata systems are unpredictable in the sense that in order to predict them perfectly, you'd have to solve the halting problem. And in order to do that, the best way is just to run it.
Do you know what they were computing there, or what those gates represented?
I have no idea. I ran across a paper that described this a couple of years ago, and I was lucky to find a clip on YouTube yesterday that actually shows it. So I don't know what they were computing there. But the interesting thing is it could be anything, right? I mean, that's a computer. It can compute anything that your computer can compute. Okay, so we've talked about how computationally complex things are unpredictable in one sense. Let me give you 4 counterarguments to that. So first counterargument is that for machine learning, there are there's several interesting theorems that show that we may not be able to predict the outcome of a computation perfectly, but we can often get very, very close with relatively small inputs. So perfect prediction might not be possible. It might be extremely difficult, but epsilon close to perfect might actually not be that difficult, depending on the system. So machine learning has some nice proofs that shoot down computational complexity as a real barrier. I mean, practically speaking, if we could predict 99.999% of revolutions with high accuracy, most people would be satisfied with that. You'd be willing to drop that last billionth of a percent. Certainly be better than where we are now. A second one is that, and I'm not going to go into this in a whole lot of detail, but encryption and a lot of other problems depend on the assumption that 2 classes, P polynomial difficult problems and then NP problems, are different complexity classes. That's actually a guess. It's a hunch. We don't know it for sure. And one of these days, somebody may come up with a counterproof or counterexample. Doesn't seem likely. There's $1 million on this, and the $1 million have been sitting on the table waiting for somebody to prove this one way or the other. Nobody's proved it. But if you came up with a proof that those 2 complexity classes were actually the same, then a lot of these problems, like the traveling sales problem that we've said are very difficult, might actually be solvable in an easier way. Third counterexample is brute force and Moore's law. So it might be the fact that computing the correct solution to a system is very, very difficult, computationally complex. But if computers keep doubling in capacity every year and a half, then pretty soon difficult problems become easy. And so it may be the case that sooner or later we'll just be able to brute force an answer to that. It's hopeful, right? In some ways it says it's unpredictable now, but it might not be in the future. The last approach to shooting down complexity as a barrier to computation is to ask, well, if you have to do all that computation to get the right answer, to predict this thing, how is the system itself performing all that computation? If it turns out that there's error or noise in there, then maybe we don't have a good description for the system. And if it turns out that the system is performing all that computation, then in theory, you just need to get a computational engine that has that much predictive power plus epsilon, and you can predict just as fast as the system can. So possible counterproofs for complexity as an argument for unpredictability. Okay, last example, and resources. This should have ... question mark here. If you have suggestions for other things on computational complexity, let me know. I think our fonts may be different, because I kept putting these at the bottom of the screen. I think some of them are getting nudged off the bottom. Okay, here's a totally different line of proof that I think is really interesting, and as a social scientist, this one is near and dear to my heart. So in game theory, which is a formal set of logic for reasoning about how people will interact in strategic situations, it turns out that you often get interactions where people have an incentive, strong incentive, not to disclose what they're going to do. In game theoretic terms, we call these mixed strategies, where you deliberately make your strategy unpredictable. So one example of this would be in football. You're going to run a play. If your opponent knows what play you're going to run, then it's pretty easy for them to stop you. So bluntly speaking, you might say, oh, you can either pass or you can run the ball. If your opponent knows you're going to pass, they can set up their defense for that, and they can stop you. If they know you're going to run it, they can set up their defense for that and stop you. So your best hope is in being unpredictable. Your best hope is in not letting your opponent know whether you're going to pass or run. Similar situations show up in a lot of places. They show up in war, right? There are a lot of different places where you might try and attack an opponent. If they know you're coming, then they can stop you, but if you can keep them guessing, then you may be able to do more damage. It turns out that a lot of other things have this characteristic too. So elections, which states am I going to spend my dollars in? Which states am I going to advertise in more heavily? That actually has a very similar underlying structure to the question of where am I going to attack an opponent. Soccer, poker, lots of these things show up. So let me give you, okay, switch the order of this at the last moment. The interesting thing here is that just because somebody wants to be unpredictable doesn't mean that they necessarily can be unpredictable. So a really intriguing thing about social systems, in fact most systems, but social systems in particular, is if you want your whole football team to run the same play, you have to tell them. At some point they have to know. And so if you have, for example, somebody who, if you know that the receiver always gets jittery on passing plays, then you can watch for that tell. You can watch for the fact that the receiver gets jittery, and maybe that lets you set up your defense a little bit differently. So if you have the capability to intercept the signals that a team is using to coordinate and translate them, then all of a sudden they may be trying to be unpredictable, but they can't anymore. It's, I think, a really interesting question, how far you can go in that direction. Is it possible to coordinate action in a way that's completely unpredictable from the outside? A really good example of this would be code breaking in World War II. So the Allies did a much better job of cracking Japanese and German codes than the other way around. And what that meant was they were able to forecast and anticipate many of the actions on the opposing side, and that turned out to be a pretty decisive advantage. But, arguably, that's why the U.S. won the Battle of Midway, which was the turning point in the Pacific. So if it turns out that people have tells, or people or teams, or whatever your actor is here, and they're unable to coordinate action without giving signals away, then it might be the case that even though they're trying to be unpredictable, they can't actually pull it off. Okay, let's see if this demo works. This is a very simple example of a game that is unpredictable, or at least ought to be unpredictable if you're any good at it. Who knows rock, paper, scissors? Yeah. So just as a simple example of unpredictability, can you predict what I'm going to do next in rock, paper, scissors?
Probably not.
Probably not?
No, I don't know. I think if you're a human, it's probably not truly random. I'm guessing you try to be random and you become correlated. Is Is that true?
If you're fully random, you have absolutely no strategy.
Yeah, but a human is not random. You're not going to put like.
No, so being totally random
rock.
doesn't mean you have no strategy, right? I'll show you an example after this where you have being random or having a strategy must involve being random. Having a good strategy.
I got one example that I played a game with my cousin. I always won 80% of it,
Uh-huh.
so I can predict what he's going to do.
Uh-huh.
So it's not totally random.
So suppose you were playing rock, paper, scissors for money, or you're playing poker or something for money. In that case, you have a very strong incentive to actually be random, right? To not give away too much for free. Yes?
So to what extent can you actually be random rock, paper, scissors? To what extent can the computer start mapping it out and undermine your strategy? Is that what you're about to talk about?
Yeah, so let's do this. Let's play against the veteran computer here. Okay, so what we're going to do is we're going to pick rock, paper, scissors. The computer is going to do the same thing. It doesn't cheat. It doesn't get to see what we do. It just gets to guess what we're going to do. So just quick show of hands. Actually, just raise your hand with the appropriate thing, and I'll try and make a guess on which one we're mostly voting for. Rock, paper, or scissors? Oh man, we're all over the place. You know what? Let's do it this way. Let's just go down the row, and you get to take a turn. Okay, let's do it this way. So, Carl, what are we doing first? You get scissors. Okay. Okay.
Yes.
Humans 1, robot 0.
Rock.
It's a tie.
Scissors.
So this computer. Paper. This computer has played tens of thousands of games against human beings, and so it has seen all of the patterns that people do. And the case that the researchers behind this make is rock.
Here
Okay.
you're not playing against one person, right? You play
Yeah, so I don't know how this messes things up.
Yes, it up completely.
We skipped you.
It's random. It's gonna be.
Scissors.
It's actually an interesting question whether the whole group is going to behave like one.
Yeah, I think that is really an interesting question. John?
Scissors.
Scissors? There's no shame in getting beat once in a while. Of course John Holland wins. It's playing a genetic algorithm, so you'd expect for John to be able to do it. Paper? So when I played this, let's work our way up from the back. When I played this with the computer, I went 200 rounds because I wanted to be statistically significant. And I lost about 60% of the time. So it wasn't a slaughter. I wasn't completely creamed, but the computer definitely beat me. Scissors. Okay, couldn't hear you. Sorry. So we're actually doing really well here. Scissors.
Computer's going to cure himself.
Dimitri? Paper.
Oh,
Down 1. Rock. Ooh, it's catching up. Scissors.
Yes.
Okay, humans 1 point. Rock. Okay, let's go through the rest of the room. And then
Yes.
good.
Rock.
yes.
Paper.
Where are your paper?
Rock.
Yeah. I knew it. Paper.
Paper.
Paper again.
I understand you, man.
And I'm going to guess scissors. Tie.
Yeah.
That's not bad. We won almost half the time. So there are some interesting proofs around this as well. So what the computer's doing here is it's looking at our past recent history. I think it keeps a window of our last 4 moves. And it says, in the past when somebody has said scissors, rock, scissors, scissors, on average, human beings usually do paper the next time around. And so if it thinks that we're usually going to do paper, it'll pick the thing to beat it, scissors, right? Now, if we were truly unpredictable, then it could never beat us. Interestingly, there are some proofs that show that in many games, if you try and psych out your opponent that way, that inevitably opens you up to being beaten. So a smarter person can take your actions and turn them inside out and use the fact that they're trying to beat you. Yeah, use the fact that they're trying to beat you to beat them.
Right.
If you want to guarantee that you don't lose at rock, paper, scissors, your best option is to find some chaotic system that's truly unpredictable and flip a three-sided coin, basically. Was there a comment or question back here?
I forget what it was, but recently someone had a camera system, that the high-speed camera, and it sees which one you're going to make, and it has a computer make the beating move. It's kind of not really related, but it's you can play it against this machine that will always beat you because it has
it just has faster reflexes. Yeah, that's cheating. That's cheating. Okay, so let me close out here.
So have you tried that generating an algorithm that's truly random just to see if, in average, if you play 200 times, it will be 50-50?
I'm sorry, say that again?
If you just do it truly random, instead of you putting paper, rock, scissors, just do it completely random.
Against the computer?
Yeah, just see if it's going to be 50-50.
I have not tried that, but I can prove that it will.
Yeah.
Right. Regardless of what algorithm you're using, if you're truly random, then it doesn't matter how they try and predict you.
Correct.
You're going to win or lose a third of the time because your actions are totally uncorrelated with theirs. Just to make this a little more interesting, I'm not going to get into this. Rock, paper, scissors is interesting but kind of boring in the sense that the perfect strategy is to mix totally randomly. You do exactly 1/3 scissors, exactly 1/3 rock, exactly 1/3 paper. There's a really interesting paper on penalty kicks in soccer. This is put out by an economist. And the logic here is, if you're a soccer player, there are, loosely speaking, 3 places you can try and kick the ball. You can kick it to the far left, or the far right, or the center. And I forget which way it leans, but one side gives the kicker a little bit of an advantage. The kicker is able to, I think, hit it harder to the left side of the goal, and most goalies have a harder time getting there. So if all else equal, if the goalie doesn't know where I'm kicking and I kick it left, I have a slightly better chance. The problem is, if I always kick it left, then the goalie just goes and stands on the left side of the goal and catches the ball there, right? But if the goalie stands on the left side of the goal, then I can very easily kick it right. Follow me?
Yeah.
So
there are some strategies of the goalie pretending to go to the left and come to the right.
Well, it turns out that you can do strategies and reflexes there, but the case that the economists make is there's no reflex to it. It turns out that the goalie and the kicker basically both have to decide before, or at the moment the ball is kicked. So there's no ability to actually respond to the other player. You just have to guess. So the instant the ball is kicked, the goalie has to be jumping one way or the other, and the player doesn't have a chance to change their strategy at that point. So if that's the case, you can go through and do the game theory on this, and it turns out that you should kick the ball to one corner or the other, but you should weight it. Depending on how strong you are as a kicker, you should kick it more to one side or more to the other side. So this is an example of a strategy that's random, but it's totally strategic, right? If you just did 50-50, you wouldn't be as strong a kicker as you could be. Your best chance is if you split it and push it more to one side or more to the other, depending on the strength of the kicker. And it turns out that if you go through and solve the math on this, it predicts a certain percentage, I forget, it was something like 71% go to the left. And if you go back and you look at actual soccer kicks in kickoffs at the end of the game, or penalty kicks rather, that prediction is almost exactly right. So whether the soccer players know it or not, they're playing the game theory out, and they're kicking almost exactly the predicted amount at the corner of the field, or the corner of the goal. Okay, so just quick discussion. I know we're on the hour, and so people need to leave. Yeah, a few questions to raise, and I'm happy to talk about other things. Oh, John, yeah.
Just a comment.
Uh-huh.
Notice that in chaos theory, and in fact with the others as well, you're assuming that PDEs are the only real way to describe the system. There may be alternative kinds of descriptions that are not PDEs, which in fact, in a common term for this is hidden variables or something like that, where in fact, by describing the system in another way, you would avoid the fact that the real system is chaotic. I'm not saying this is so, I'm just saying that this is, physicists' hubris, that the systems of interest can always be described by PDEs.
Yeah, another way to say that you have a phenomenon, you have to create a description, and the description can be chaotic or not, right?
Exactly.
And whether this is the only description for a phenomenon is another question.
So this is kind of a deep philosophical question, but if you believe that that a chaotic set of equations is is a true description of a system, then I think it follows that any other description is going to be isomorphic to the chaotic system, and then you're wrong. But, for example, I talked about error bounding theories for machine learning. A lot of those turn on the idea that you can take another interpretation of the problem that's epsilon close to the first one, and even if the first proof of the problem, or even if the first system is computationally complex, something within epsilon, a very, very similar description of the problem, might actually be pretty simple. So I think that's an example of what you're saying. If you don't believe that the chaotic or the complex or the mixed strategy interpretation is the right one, if you just think that it's a pretty good approximation, it may be the case that there's another very good approximation that isn't so hard, that isn't so unpredictable. Is that a fair way of saying what you're saying?
There's a supposed proof in quantum mechanics that there can be no hidden variables that will get rid of the uncertainty. But in fact, that again makes a very strong assumption about the wave equation and its quasi-linearity. And so that proof is only a proof as long as you believe that the wave equation is the true description of the phenomenon. So, as you say, it's a philosophical point, but sometimes it's worth you want to back off of it and see if you can think of another way to get into the system.
Yeah, I think that's right. So that actually speaks to some of these questions that I thought would be interesting to talk about as a group. The first one is, just generally speaking, are there problems like this that seem like they might fall into this category of things that are fundamentally unpredictable? And if so, why? The second one, I think, is more what you're raising. Given that we encounter a problem like that, what do you do as a scientist? Do you just give up and say, can't do it? Or do you say, maybe there's an approximation of this problem that comes arbitrarily close, and it turns out to make it tractable all of a sudden?
I think in regards to the second bullet point, the idea of how we represent reality, what our models, what we capture from the observables in reality is very important. For example, going to the PDEs that we were speaking about, fundamentally they're all approximations. They're all wrong because we're assuming continuity in reality as far as being discrete. So perhaps we could go farther. We could have a different representation that they assume continuity and whatnot. So then if we're faced with a problem that seems apparently unpredictable, we should step back and say, well, really, am I just doing the best that I can because, say, there's a huge ensemble of particles and I can only take averages or else it would be intractable? Or can we do a little bit better? It's an issue of computation, it's an issue of representation, stuff like this.
Yeah, that's a really good point. Let me put some teeth in this question. The Lorentz equations, right? These were discovered early on in the study of chaos, and they weren't intended to be chaotic. They weren't discovered as an example of chaos. They pop out of the natural way that we were representing weather flow at the time, right? I don't remember all the details, but 3 continuous variables that describe the state of the weather on any given day, right, as a dynamic system. Do we think that we're actually going to be able to predict the weather someday, right? If you think that that's the right interpretation, then it follows that weather is unpredictable and we throw up our hands. Do you really think that we might be able to get around that somehow?
I think so.
You think so?
Yeah. So I think it would be a matter of computation. I mean, at some point, if we had, say, a quantum computer the size of Australia, and I'm assuming that's possible, and we could model all the particles surrounding the Earth up to some degree, up to some threshold.
Well, so the problem
that with some horizon, I mean, clearly.
The problem with forecasting weather isn't not knowing how it's going to behave. We can actually see all of those variables and measure them with reasonable precision. The problem is we believe that the Lorentz equations are actually a pretty good description for how that system unfolds. And so it's a problem of measurement, right? It's not a problem of computation. It's a problem of can we measure the current state of the atmosphere to arbitrary precision.
But I would think that hopefully we have better computational methods and we can measure more precisely. Those are independent problems.
Okay. Other thoughts?
Well, also it seems like, speaking of the weather in particular, there's sort of we get to keep kind of supplementing measurements with updated measurements. So it's not like, so in some sense, it seems like, even if it is chaotic, because we get to keep measuring.
So we're observing enough history.
Well,
it's not about a point prediction or a point measurement.
Right, we don't need to predict the weather forever from now. We could, if we predict the weather for a week from now pretty well, then we can remeasure, and even though our errors have grown.
Well, that depends on what you're going to do. That depends on what you're going to do. So there's a very interesting business called weather insurance. The idea is if you're hosting a marathon or a wedding or something that's going to be outdoors and it's going to get rained on, then
you put your money that it's going to rain.
Yes, you short sell the rain, right? And in that case, if it rains on your parade, you're not totally out in the cold, right? It's a way to hedge risk. Now, in theory, if you could predict the weather, people will take out these contracts many months, even years in advance. If you could predict the weather, you could make a lot of money in that market.
Yeah. Well, it seems like in that case, you'd want to price it based on how much computational power you're going to have to spend predicting that far out. So if you want weather insurance for 5 years, it's going to cost you. If you want weather insurance for tomorrow.
That's really interesting. Yeah, the risk is going to be a direct function of the economic.
I think that's the point that he's making is that even if you spend all the money that we have, we currently can't predict the weather in 2 years.
Right. I mean, you can predict certain things about it. You can predict it's going to be colder in the winter and warmer in the summer. But, you can't predict if it's going to rain on Tuesday.
I think it always, I mean, somehow, this could be wrong, but it would always come back to having sufficient information, being able to properly process that information. For example, trying to predict the revolution. If we had, let's say if we had access to the diary of every single person on an island, so we're trying to, maybe Australia again, it's fun. So we're trying to predict that there's going to be a revolution in Australia, and we have access to the diary of every single individual. Perhaps that would be sufficient information to properly predict the revolution. Certainly, we also need to, these are...
So if the revolution's going to happen tomorrow, right, and some people are in on it and other people aren't, then I'm willing to go with you there, right? If we can see all of the organizers' memos, this is why it's a little bit worrying that Iran and China are like monitoring social media so much, right? Because it becomes very difficult to coordinate a revolution or any kind of social action without the government down. But if we're trying to predict a revolution in Australia 20 years from now, I'm not sure that knowing everybody's diaries to immense detail today allows us to predict that.
And that's where I would say it's insufficient information. And so the farther off we go, the greater the horizon that we want to predict, the more information we need. And if I want to predict the revolution within 5 seconds, I should just probably look west a bunch of weapons and really militias. Like,
right. There we go.
So yeah, we all know that. But there's this inverse relationship between the amounts of, actually there's a direct relationship between the amounts of information necessary and the horizon.
What looks like most of the nonlinear equations we use, right? That exactly you can look in a short window that is close to your initial conditions.
Right.
That's the point he's making.
Right.
Yeah. I think what you said translates to you believe that revolutions are chaotic, and over some event horizon, it's going to be basically impossible to predict them.
Unless you had absolute information.
Yeah,
it's
but
the same chaos.
I feel like that's a pretty safe assumption, that we're not going to have perfect information ever. Okay, safer claim, we're not going to have perfect information within my lifetime, and so I'm okay asserting that.
Or somewhere else.
I think a lot of this depends on whether you believe the world is deterministic or stochastic.
I should have said this more clearly. The really intriguing thing about chaos theory is
It's
that
deterministic.
it's perfectly deterministic, and yet it's unpredictable. There's nothing stochastic about it.
It kind of depends on what you define as predictable. If you say that you know exactly what the initial conditions are to the exact decimal point, then of course it's predictable. It's completely predictable if you're going to do that in the exact same way.
I think the mathematical prediction is again coming back to the error, right? Like if you don't wanna run the whole code and see, let's run the code and see in 200 years what's going to happen. Let's try with no information to guess what's going to happen.
Yeah.
And then you can measure.
Just to be precise on this, I'm trying to make a logical argument that has two assumptions. The first assumption is the system we care about is chaotic. And you're right that if we know initial conditions, then that's a totally predictable system. But the second assumption in my argument is we can't measure initial conditions perfectly. That seems like a pretty safe assumption a lot of times. And if you believe both of those things, then that system, system X, is unpredictable beyond some horizon. So you're right that a chaotic system is, in a sense, it's deterministic. It's totally predictable.
I think the failure of being able to get that perfect decimal point is a feature of human failures in general, like the ability to somehow constrain my human ability to get that perfect decimal point. Or is the world itself actually stochastic? Do you believe it?
I see. That second assumption, we snuck a tiny bit of stochasticity back into it. That's a really interesting point.
Yeah, I think that's the central design, because I fully agree that all of these systems are chaotic within our definition, and certainly the logical argument that you propose, it follows that there will be unpredictability. But then the argument is, well, if we gathered more information, can we predict better? And then how far can we take that? Is it possible to go to some extreme? And if it's not, then we must accept that. Why? Why is it? Because we have the failure in being able to observe reality, or because reality itself is, you somehow cannot understand all information. And I think perhaps that might be it.
Yeah, I mean, we've kind of made a full loop here to a deep philosophy of science question, right? Is it possible to predict anything with perfect accuracy?
Or whether your second assumption can be changed. Whether we can measure anything.
Is it possible to measure anything with perfect accuracy?
Yeah.
I guess I'm enough of a pragmatist to say, I don't know, but I haven't seen it yet.
Right.
And I don't expect to see it.
There is nothing that prohibits, as far as you're not talking about quantum mechanics, what is not the case. So in physics, anything that you're not down to the level of atoms, in principle you can measure, in principle you can get information. So there is not a physical prohibition. So nature
Which, by the way, is why I said I don't know about the revolution, because I thought, well, maybe the information at the atomic level is irrelevant to understanding the behavior. So maybe the closest. But I mean, if we need to get down there, then
I have a guess. It's pretty relevant.
So I'm going to chicken out on this one and not answer the question directly and just say, as a pragmatic thing, I don't know of really any perfect measurements, and so I feel pretty safe making a second assumption a lot of the time.
What if the question itself can't be answered because we have enough information? I don't understand.
You don't understand because we don't have enough.
Right.
All right. Thanks for coming. I hope this is interesting. I hope this is useful. If you have suggestions for other things to fill in, resources, I'd love to hear them. And just to put in a plug, I think sometime in the near future, next session or the one after, I'm actually going to get to present on my research on civility and political blogging, big data stuff. So that'll be really fun. Yeah, cool stuff.